Okay, sir.
Topic now there. What part also I'm going to recap. Okay. So today, good afternoon now. So today I'm going to talk about frequency response analysis. This is a very useful technique to analyze the system to design assess the performance stability and other performance parameter. So like what are the frequency plots means?
Phone polar
plot, equals plot.
Phone
And before that, we are going to know that types of frequency domain specifications. The first one, frequency domain specifications. Okay, the first one, gain margin. This is very important. It is denoted by Bode. Then phase margin is denoted by gamma. Then gain crossover frequency, that is omega GC. Then phase crossover frequency, that is omega PC. Then resonant peak, it is denoted by gamma. Then resonant frequency is denoted by omega. Then bandwidth is omega p. Then cutoff frequency or corner frequency. Cutoff frequency or corner frequency. These are all the important time domain specifications. Okay. So apart from this, the gain margin, phase margin is very important specification to assess the system stability. Gain margin, phase margin both are positive means system set to be stable. Any one negative or both are negative means the system set to be unstable. Okay. Then bandwidth is very important to very important index to assess the system response. Will be the response that is related to the rise time. The rise time lesser means system response quickly. Rise time larger means is low response. Okay. Now let us discuss Bode plot. This is a frequency plot. There are two plots. One is magnitude plot. Magnitude plot, other one is phase plot. So magnitude plot, that is a log omega, that is frequency versus magnitude in dB. This plot is frequency versus magnitude in dB. That phase plot is a frequency versus phase angle. Frequency versus phase angle. Now let us discuss one by one. Procedure to how to draw the Bode plot. Procedure for Bode plot. First, you should know that the transformation contain various factors. One is constant gain, other one is first order differential function. Okay, then in numerator, similarly integrator, in denominator, the second order term in that is quadratic function. Term in numerator, then second order term in denominator. Okay, so these are the some basic term which is present in the given transfer function. Based on that, we can do the steps to plot the Bode plot. First, let us consider the given transfer function g of s h of s is equal to say k divided by say something instead of k say take 10 s into s plus 2 into s plus 3. So let us consider this transfer function. So how to plot the Bode plot and find the frequency domain specification like gain margin, fixed margin, and gain crossover frequency, fixed crossover frequency. So first, the given transfer function already there is a factor term that is pole zero form. Suppose it is a polynomial piece, you should first convert given transfer function into pole zero form, polynomial into pole zero form. Then letting s is equal to j omega. Letting s is equal to j omega. Now we get the transfer function in frequency domain. So this is an S domain transfer function. So g of j omega and h of j omega is equal to wherever is s, let s is equal to j omega. So j omega. Before that, you should convert this modular form into time constant form. Time constant form, that is 1 plus st form. So now we need to convert this transfer function into time constant form, that is 10 divided by s into the denominator and the second term is there, we make it to 1. So 1 divided by 2. So 2 is taken out. 1, 2 by 2, 1. That is s by 2. In third term, 3 is taken out. 1, s by 3. Okay. So 2 into 3, 6. So 10 by 6. Out of the numerator. So s into 1 plus 1 by 2 is 0.5s. Numerator. Similarly, 1 by 3 is 1 plus 0.33 yes. Okay. So this is your g of s, h of s. Okay. Now letting s is equal to j omega. I can continue here. So g of j omega, h of j omega is equal to 1 by 6. Wherever it says replace this by j omega, 1 plus j 0.5 omega, 1 plus j 0.33 omega. Okay. Now this is in rectangular form, this complex transfer function. Now convert it into polar form. How do you convert? Say z is equal to x plus jy. angle theta is equal to tan inverse of y by x. So modulus of z angle theta, this is the polar form. So like this you have to convert this rectangular form into polar form, this transfer function. The numerator there is no imaginary term, the only constant real term square. Take the square at then apply square root, so you get the same function. So modulus of g of j omega h of j omega is equal to 10 by 6. For this term, x will be 0, that is real term will be 0. Then square omega, then taking square root, you will get only omega only. For this term, this x plus y, like real and imaginary term. So square root of square of 1 is 1, then 0.5 omega whole square. And the third term, the denominator, again square of 1, again you get 1. So this 0.33 omega whole square. So this is for magnitude form for the given transfer function. Similarly, we need to represent again phase angle form. Okay. For numerator there is no imaginary term. So 0 by 0 is 0 initial angle. Angle of g of j omega, h of j omega is equal to numerator. We have angle 0 because there is no j omega term, imaginary term. For denominator, real term will be 0. So omega divided by 0 is anything by 0, infinity, tan inverse of infinity is 90 degree. Okay. Then this one. Tan inverse of y by x, that is 0.5 omega by 1, again same 0.5 omega, again angle tan inverse of 0.33 omega. Again this denominator angle brought to the numerator. What do you get? Minus 90 degree minus tan inverse of 0.5 omega minus tan inverse of 0.33 omega. Okay, this is your phase angle of given transfer function. Now we express gain, and before that we need to find the corner frequencies. That is, example, g of j omega t is equal to j omega is equal to 1 plus j omega t means how to find the corner frequency. Omega c is equal to the coefficient of real part divided by coefficient of j omega. Okay. So 1 divided by t. The same way, find out for the numerator there is no imaginary term. Denominator the real term for the first term, real term will be 0. Only the second term and third term we have corner frequencies. So what is omega c is equal to like this, 1 divided by coefficient of j omega 0.5. So 2 radian per second. Then omega c is equal to 1 divided by 0.33. So 3 radian per second. Now assign the number, assigning model, this is omega c1, this is omega c2. Apart from this, we need to choose this is calculated corner frequencies. We need to choose two more corner frequencies, that is omega n and omega h, lower limit and higher limit corner frequency. Okay, so what is the rule for selecting lower limit and higher limit corner frequency means the lower limit corner frequency which is lesser than the least value of calculated corner frequency. So here omega c1 is 2, so you can choose the lower limit corner frequency less than this. So generally omega l to be chosen less than 1 for the better choice. So we can say, you can select uptake. So omega n is equal to 0.5. You can take some other value also. Instead of 0.5 you may take 0.2 or 0.4 or 0.6, whatever it is. Okay. Similarly, higher limit corner frequency which is greater than the highest value of calculated corner frequency. Here omega c2 is 3, so you can select next immediate high value. Say instead of 3, immediate high value 5 or 8 or 10. Okay, say omega x is equal to taken as 10. You may take 5 or instead of 10, you may take 5 or 8 or something. Don't take too much value. So that's just higher than that calculated one. Now using these corner frequencies, we have to calculate gain in decibel. What is gain? Gain A in dB, decibel. We should express into decibel. So gain A is equal to 20 log modulus of T of j omega h of j omega. Okay. Now letting various values of omega, that is corner frequency, we can calculate in decibels. Okay. Now find the gain for various corner frequencies. So gain in dB. So A is equal to 20 log modulus of T of j omega h of j omega. Okay. Now substitute 20 log modulus of this, that is 10 divided by 6 omega into square root of 1 plus 0.5 omega whole square, again square root of 1 plus 0.33 omega whole square. Okay. Now at omega is equal to omega n. So that is here chosen. Lower limit corner frequency is 0.5 radian per second. Okay. So this can be easily calculated using calculator Casio M991MS model. Now replace this omega by assigning some other variable. So like this you can express this equation in calculator using Casio 991MS model. Okay. So how do you express means 20 log bracket open 10 divided by 6, 1.667, 10 by 6, that is 1.667, so 1.667 divided by, again bracket open, this instead of omega, so I can put A or X or something, okay, X, so you will get this variable calculated by pressing alpha. Alphabets, then press close parenthesis. Okay. So then square root, again bracket open, 1 plus, again bracket open, j 0.5 instead of omega again put x. How will get x now? Plus alpha and close parenthesis, okay, square. Again close the bracket. Here one bracket is open. The next, then 1 plus before that. So you after typing this square root means immediately open bracket 1 plus okay 0.33 x whole square. So close this bracket. So already here we open two more bracket. Now close this. Okay. Now this expression titled like this using ACO 991 MS model calculator. After typing this equation plus now I'm going to type this calculator. After this typing this equation using calculator, then plus calculate Bode. So now display, the calculator display shows that x value, you have to give the x value. So we have chosen x here, omega times x. So now substitute the x value is 0.5, then plus equal. What do you get? So you will get gain A is equal to 10 dB. Similarly, at omega is equal to omega C1. So omega C1 is 2. Now substitute again 2 plus equal. Now again d value. So you will get the corresponding gain for omega. This is for omega L. This is for omega C1. 2 corresponding gain is minus 6 dB. The next plus at omega is equal to omega C2, that is 3 radian per second. So substituting 3, so you will get gain. Gain A is equal to 13 minus 13 dB. Now plus we have taken higher limit corner frequency. Omega x is equal to 10. Say for 10, so minus 40 dB. So this is the gain in dB for various values of corner frequency.